Hey everyone, how's it going? Can you all hear me okay? You can do it here. Sweet. All right. Hey Alice, thanks for letting me know. As always, well done to everyone for getting the motivation to do physics on a Sunday afternoon. I think that's pretty good going. So today we're doing moments and resistive forces. Um, so we'll actually do the resistive forces stuff first, and they're pretty much separate topics. So we're going to be doing two separate shorter things today. Hey Reza, hey BTS, how are you doing? Are we all in first year, second year of A levels? How are we finding physics? Have we seen this before? Moments and resistive forces? Either of them being kind of two separate things. Tomorrow you have a test of the same topic. That's perfect. Which one, the moments bit or the resistive forces bit? Yeah, and good. Yeah, good point. Good luck. Good luck for the test. I think moments is quite a nice topic in A level, actually. Um, yeah, I quite liked it. It's one of the ones I preferred doing exam questions on, actually. Oh, okay, so you have both. Perfect. And pressure and density. Okay, cool. All right, we should get started, bearing in mind I started slightly late as well. So you should all be able to see my notes. In fact, I can see that you can. You should be able to see me writing as well. So let's get started. Today's moments and resistive forces. So just a quick thing about me. So this is me a couple of years ago now. So my name is Matt, head of physics here at Snap Revise. Currently doing a physics PhD, although kind of undercover. It's actually a computer science PhD, but I mainly think about physics stuff. Okay. And yeah, I've been tutoring physics for the last 4 or so years. So just to let you know, there's a code here. So if you want to see all the stuff we're doing on the Snap Revise website, because what we're doing on YouTube is just like a bit of it. So if you want to see all the courses that we're doing on the Snap Revise website, you can currently get a 25% off code. So you can see it here now, and it will be up at the end of the session as well. Okay, so back to the main event. The objectives today are to explain the effects of resistive forces on bodies in motion. So we've got something that's maybe moving through a fluid like air or water. And we want to talk about the resistance to motion that you get as a result of doing that. And then we'll talk about rotation. We'll talk about the kind of rotational version of talking about forces, and that's called a moment. And essentially, we'll then do a load of calculations with moments, including determining if systems are in rotational or translational equilibrium. So that's the kind of moments versus forces part going on. Okay, so maybe we don't, maybe we know this, maybe we don't, but here are the kind of things that we're going to be relying on for today's session. So the first things we're going to need to know are Newton's laws. And in particular, I'm going to need to know about Newton's second law. So can anyone tell me what Newton's second law says? In fact, while you're doing that, I'll write down Newton's first law, which you can derive from it. So Newton's first law says that when the net force is 0, the velocity is constant. So we've got some object that's moving around, maybe with some velocity. And what I'm saying is, if you don't push it with some force, then it will just continue going along in that velocity forever. Okay, good. Newton's second law, which actually implies the first law, Newton's second law says that force is equal to mass times acceleration. And the way that it implies the second law is, well, if the force is zero here, that would mean that the acceleration would be equal to zero from this equation. And that's the same as asking for the velocity to be constant. Good. Force is directly proportional to rate of change of momentum. Yes, so that's the super general version, which we won't have to use today, but that is technically the most correct one. Absolutely right. Good. Okay, so the second thing we're going to need to talk about is vectors. And the reason for that is forces, for example, that we're already talking about, are vectors. They're things that have both size and a direction. So let's say I have some forces or some other vectors, T1, T2, some weight here. And I want to add them together to find the net vector. That is the result of adding all these vectors together. How do I do this? How do I add vectors together? So this is kind of a vague question in a way, maybe. I'll say that graphically, what it amounts to is taking the tip of one vector and putting it on the tail of another vector. So it's like we take this bit here and we attach it to this part here. So that's what we've done here. This is T2, and then we've just put T1 on the end of T2. Actually, we could even add in W by putting W on the end of T1 or at the start, wouldn't matter. Either way, you add up the vectors by putting them all end to end like this. Now, this is quite a special collection of vectors because when I added them all together, I ended up back where I started. So that means that the net vector here, the net force, if you like, is equal to zero. So this is exactly the kind of situation in which you would have no acceleration. Okay, often we call this equilibrium. There we go. Okay. So the other thing we're going to need to be able to do with vectors, rather than add them together, is to split them into parts. So let's say I have a vector here. It's at an angle theta to the horizontal. I want to know what I want to call the horizontal component. So I can split this vector into two parts, a kind of vertical part and a horizontal part. Let's call them X part and a Y part. So how can I find the size of the X part, the horizontal part? Well, I can do that by taking T1 and multiplying by cosine of this angle theta. Similarly, for this vertical one, I can take T1 and multiply it by sine of this angle theta. So that's how we split them into parts. Okay, so that's general stuff about forces. Now there's a particular type of force, which we already kind of mentioned here, called the weight. Now, does anyone know the formula for the weight? The weight is, I'll mention it here, it's the force on a mass m due to gravity. But what I want to know is what the formula is. If I tell you the mass, how do you calculate the weight? Good, W equals mass times the acceleration due to gravity. So this thing here is 9.81 meters per second squared. That's just a number it's worth kind of keeping in your head, but it might even be in your formula book. Yes, okay, good. So the idea here is we've got some mass m, and the force is a vector pointing down, and that thing we call the weight. And its size is given by mass times gravitational acceleration. Okay, good. So notice, finally, that since F equals ma, then the acceleration equals force over mass. So if your only force is the weight, then your acceleration is mg over m. That is, your acceleration is g. That's why we called it the acceleration due to gravity. And as it doesn't matter how big your original mass was, those masses factored out. So your acceleration is always the same. It doesn't matter what mass you have. Okay, so that's stuff that's going to be handy to know today. Here are the spec points that we're going through for the 3 main exam boards. Okay, so this is pretty popular stuff with all the exam boards. There we go. And now let's get started. So we'll start with resistive forces. Okay, so what's a resistive force? Well, I'll jot down a definition and then we can discuss it a bit. Resistive forces are forces which, and here's the key word, which oppose the motion of a body. Okay, so what direction should the force be pointing in? Let's say I have a body which is moving with some velocity v. Then, okay, resistive forces have to oppose the motion. That means a resistive force should always point in the other direction. Okay, so let's jot that down. That's an important point. So always in opposite direction to motion. Okay, kind of sounds like the first one. Okay. We often refer to them as causing a deceleration as opposed to causing an acceleration. So sometimes when a force is slowing something down, we say that that thing is decelerating instead. Okay, so there are 2 classic examples of resistive forces: friction and drag. So the difference between friction and drag is the kinds of things that you can have friction with and the kinds of things that you can have drag with. So maybe have a think about that. I'll start writing down the definition of friction. Friction is the resistive force due to contact, that's a keyword, contact with a surface. So essentially, friction is usually about interacting with solids to start with. So here's a block. Let's say it's got some mass m, and it's in contact with some kind of a surface here. And as a result, it has some kind of friction. And what that friction will do is, let's say the block is moving with some velocity to the right. Essentially, all the bumping into the particles, all the rough edges on the surface here, causes a load of collisions, which are always trying to knock the block backwards a bit. Okay, we end up calling this thing friction. Okay. Now, the interesting thing about friction is it can be there even when an object isn't moving. So can act on stationary bodies. So a classic example of this would be something like a block that's on a slope. Now, if there was no friction, then there'd be a force, a weight pulling this thing down, a component of that pointing down the slope, and the block would just slip down the slope. There's no other forces. However, when there's friction, the block might not even move. So friction can actually stop the block ever even moving. And that's something you don't actually get with drag, which is the second type of resistive force we'll look at. So this one is caused by moving. So here's an interesting question. I want to say it's moving through a liquid or a gas. So does anyone know a word I can use for a liquid and a gas at once? So anything that's not a solid. So caused by moving through a something does not act. It also does not act on stationary objects. Yeah, nice. Really good. Yeah, we call things that are either a liquid or a gas, but we don't know which, we can call them fluids. So we can kind of consider drag like fluid friction, but it's a bit dangerous too because of this second point. So if you're wondering about that, just look at the second point here. Friction can act on a stationary body. Friction can stop something from even starting to move, whereas drag only acts when an object is actually moving. So that's the difference, if you like, between drag and friction. Okay, good. So classic examples of drag would be things like an aeroplane that's moving through some air particles here. As it moves into all the air particles, it bumps into them and transfers some forward momentum to them. And as a result, they impart some kind of backwards momentum to the plane and it starts to slow down. And that's the force. Okay. So let's look at some of the factors affecting drag. So it's quite an important force. It's always there if you're trying to consider how best to engineer, for example, things like vehicles. You often want to reduce drag as much as possible. So let's have a little think. What are the factors that affect the size of a drag force? So remember, drag is caused by bumping into the object that's trying to move. It's bumping into lots of air particles. So how can we increase this force? Okay, well, number one, or decrease. Number one is to increase the velocity. If we move faster through a load of particles, then we'll be bumping into more of these particles per second, so we'll be feeling a bigger force. So bigger velocity, bigger drag. What might this picture represent? There's something about this object here that means, in a way, as it tries to fall in this direction, it feels a lot of drag. In kind of casual terms, you might say it's not very aerodynamic. Like what is it about this object that means it's going to bump into a lot of particles below it? Yeah, nice. It's got a big area here. There's a big area in the direction of motion. So, let's say size of cross-sectional area. So if you're wondering what cross-sectional means, it just means the area that's in the direction of motion. So for example, if a block is moving in this direction, this would be the cross-sectional area. Whereas if a block is moving in this direction, this would be the cross-sectional area. And that's the one that matters for the size of drag you're feeling. Okay, finally, we can think about something called essentially like the thickness. But this is a casual term. We can think about something like the thickness of the fluid. So for example, I mean, you may have said if you've ever tried to walk with your legs moving through water, you'll notice that it's harder to do that than it is to walk your legs through air. And you might even imagine that if you tried to walk through honey, it would be even harder than walking through water. So this is essentially because in a kind of informal way, each of those fluids is thicker than the one before. And yeah, the kind of fancy physics word that we're using for this notion of thickness is called viscosity. So the more viscous a fluid is, the less easily it flows and the less easy it is to move through it. So honey is very viscous and air is barely viscous at all. Okay, so last part of learning for resistive forces before we have a go at some questions. We're going to talk about a concept called terminal velocity. So I'm going to give away the punchline before we actually talk about the process, just so you know what we're aiming for. So I'm going to define the terminal velocity first. The terminal velocity of a falling body is the constant speed it reaches because drag is equal to weight. So here's the idea. We're going to get to a situation where we have an object moving through some fluid, and it's got a weight pulling it down, and it's got a drag pushing it upwards. And because these two are going to be equal, that's going to mean that the net force is going to be 0. And so as a result, the velocity will be equal to a constant. That is, the velocity won't be changing. So this is the point that we're going to try and get to, and we're going to see how we get there from a situation in which the drag is actually much less than the weight. So let's imagine I just release a ball from rest from a very big height. So at the start, there's a force acting on the ball. What force is acting on the ball? Well, just as I let go of it, it's just sat there in the air, and then, well, its weight starts to accelerate it downwards. So, okay. Ball will accelerate downwards due to weight. Okay, so somehow drag's going to get into this. Well, if we're accelerating downwards, what does this mean? Well, this means we're starting to develop some kind of a downwards velocity. So as we develop this downwards velocity, what's that going to cause? Well, we're moving through a fluid, so that's going to create some kind of a drag force. We're not moving very fast yet. So as a result, the drag force isn't going to be very big. So, okay. Motion in air causes a drag force upwards. So now we've got a little drag force upwards. What can you tell me about the resultant force on the object? Originally, the resultant force here was just the weight, and it was just pulling us down. Now what have we got? The new force overall. What's happened? Well, now the drag force is pushing up, so it's taking out a bit of the weight that's pulling us down. It's acting against that. So actually, our new net force is the weight minus the drag. It's going to be a bit smaller. So, okay, the force has got a bit smaller. Well, that means the acceleration is going to get a bit smaller as well. Okay. So, what does this tell us? Well, as the drag force opposes the weight, the acceleration decreases, but remains downwards. So let's look at this. Okay, maybe we have a smaller acceleration than we have before, but still the net acceleration is downwards. But here, what does that mean? Well, that means we're still going to continue speeding up in this direction. We're still going to get a bigger and bigger velocity in the downwards direction until eventually the velocity is so big that because drag increases with velocity, the drag can balance the weight. So eventually, the velocity is so large that the drag balances the weight. And since the drag balances the weight, acceleration becomes 0. And so velocity remains at this value. So once we reach the velocity where the drag balances the weight, well, the acceleration is 0, so we're not accelerating anymore. So the velocity is going to stay at that same velocity, and the drag will balance the weight forever and will stay at that same velocity forever until eventually this ball goes along and hits the ground or something. Okay, so how are we feeling? We have a couple of questions to look at with this stuff as well. So we will have some chance to try our luck with an exam question. So yeah, just let me know how you're doing. Straightforward, nice. No worries if it's not at all. All clear, cool. And yeah, just do let me know if you have any questions. In the meantime, let's have a go. Okay, a steel ball is released from rest above a cylinder of liquid, as shown in figure 3. The ball descends vertically in the air, then in the liquid, until it reaches the bottom of the cylinder. Okay, so we have this ball here. It's going to fall, it's going to hit the liquid, and then when it hits the liquid, well, it's going to continue falling. Okay, so that's the whole story. The idea of this is in this question, we're essentially going to ignore drag here. This question is all about the kind of proper, like, large drag that we notice here when we move through the kind of the thicker fluid in the liquid, if you like. Okay, so I'm going to redraw a picture here of the situation. Here's the ball, here's the fluid, here's the ball falling. Okay. Figure 4 shows how the velocity of the ball changed after it was released. So first of all, notice that as this ball is released, it's going to fall, and the velocity seems to be increasing. So the first thing we need to notice is that they've taken the downwards direction here to be positive. Because as this ball is moving downwards, they've said the velocity is going upwards. It's getting bigger and bigger. Okay. Now, describe and explain how the acceleration of the ball changed after it entered the liquid until it reached the bottom of the cylinder. Okay, so we're going to have to describe 3 things and then explain each of these 3 things. So maybe we'll be able to fit these all on one page, we'll see. So I think we should try and describe up to T0. Then we should try and describe maybe what's happening here in this kind of curvy bit. And then maybe we should describe what's happening at the end here. So those are our kind of 3 things to describe and then explain. So, okay, in the first section, we notice we have a straight line. Now, acceleration in a velocity time graph is the gradient. So what we can say at the start is the acceleration is constant up to T0. Okay, now we should explain why. Well, why would the acceleration be constant? That means the force on our object is constant. Well, before we hit the water, what forces do we have? Well, I guess this really means we can kind of ignore drag. If there's a constant force, it must be that the only force here is the weight. So this is because the only relevant force is the weight. Okay, good. So let's look at the second section then. So in the second section, suddenly our acceleration becomes negative because our gradient, well, our acceleration suddenly points downwards, which in this diagram means it's actually kind of pushing the ball back upwards. So let's write this here. When When we end up under the fluid, downwards was positive, we got a negative acceleration. So our acceleration is in this upwards direction here. So what does that tell us about the forces on this particle? Well, we know it's still feeling a weight mg, but if its force and its acceleration is upwards, that must mean that the drag in the liquid is actually bigger than the weight. So let's jot that down. So after t naught, the acceleration becomes upwards. This is because the velocity of the ball in the fluid, in the liquid, if you like, produces a drag bigger than the weight. Okay, so finally we've got to look at this last section, because in this last section we see that things are starting to flatten out. So we're starting to tend towards one particular velocity. We're getting closer and closer to it, and we're not really moving away from it. So what kind of name do we think we could give this velocity that we're tending towards here? There's a special word for this kind of velocity. So I'll let you think about that, put it in if you think you know what to call it, and I'll start putting in the description. So eventually, the acceleration decreases until it is 0. Well, we saw this happen before. Yeah, this was the terminal velocity story. You have two balances, and then you have two forces, sorry, and as the velocity changes because of the imbalance between the forces become more and more balanced. So that's what's happening here. It's just that we're approaching it from the other direction. This time, the drag is bigger than the weight. As a result, we're going to slow down. And as we slow down, the drag gets smaller until it equals the weight. So this is because the ball will slow down until drag equals weight. There we go. So that's quite a big question, a lot of concepts in there. Hopefully that is all making sense. And of course, let me know if you have any questions. Now, that was all resistive forces. I promised we'd look at another topic. So we're looking at an entirely different topic now, a topic of rotation. So it's still mechanics. And they'll probably come near each other in your textbooks. So the idea of a moment is it's essentially the rotational notion of a force. It's the thing that causes rotation, just like a force causes movement. So velocity should be increasing with the slow rate. So the velocity is actually going to be decreasing here. So the velocity, originally the ball is moving downwards through the fluid. But then because the drag is bigger than the weight, that means the acceleration is upwards. So this velocity here, which was downwards, is going to have to decrease a bit. So that's why it's falling. The velocity is downwards to start with. So like this here means a large downwards velocity, and later on we have a smaller downwards velocity. Okay. So let's go to moments. So we need to define a moment. The moment is the bit of a force which is genuinely causing rotation around some point. So let me write this down. The moment of a force about a point is the product. So here's the definition. The product of force and perpendicular distance. Okay, so let's see how this looks. Perpendicular distance from what? From its line of action. Okay, so let's see this in a diagram. Here's an extended object. So we've got a whole square made of some mass here. And there's a place from which its weight is acting. So here's its weight. And we want to know its rotational effect about this point here. Okay, so what we do is we draw the line that represents the line the force is acting on. And we just find the shortest distance between this point and that line. Let's call this distance x. Then the moment is given by the force multiplied by that distance. So here it would just be the weight multiplied by this particular distance. This x here is the perpendicular distance. And we call it perpendicular distance because this angle here is always a right angle. Okay, so a couple is a special type of moment. So a couple, well, essentially a couple is a pair of equal opposite forces. And then, so you might usually imagine that a pair of equal opposite forces should do nothing because they just balance each other out. When you have an extended object, they might be acting at different parts of the object. So we've got a force here acting on the bottom, force here acting on the top. And these are going to cause a rotation. The object's going to try and spin. So the spinning effect is called the torque. So the torque here is defined as the magnitude of either of the forces times the distance between them. This might seem like a weird thing to write down. Well, essentially the torque is just a fancy word for the moment caused by these forces. So the torque, as we've defined it, is the moment around any point. So as an example, imagine we looked at this point in the middle here and we calculated the moment. Well, one force is making a moment of F times, well, this is halfway, so this is F times D over 2. The other one is making a moment of F times D over 2. And they're pushing in the same rotational direction. So altogether, the total moment is FD over 2 plus FD over 2, which is indeed equal to what we call the torque, F times D. Okay. So now you may have noticed at the end there, I started adding moments together, but I wasn't very careful about that. It would be okay if you're quite suspicious about how I knew how to add them together. So now we're going to say this. We're going to say the rule for adding moments together, for finding a resultant moment, is we take the difference between the sum of clockwise and anti-clockwise moments. Okay, so let's see how this works. So let's imagine I have a load of forces acting on an object. We've got some that are pushing it clockwise, and I add these together. I add those moments together. And then I'll have some others. So let's say I'm caring about this point here. I have some others that might be pushing it anti-clockwise, and I have to add those together separately. Okay. I actually said those the wrong way around, but anyway. Okay. So let's then state why we care about moments. We care about forces because when the forces are all balanced, we get a constant velocity. So the same is true for moments. When the moments are all balanced, that is when the resultant moment is equal to 0, then the object will continue to rotate at the same rate. So the principle of moments states that when the resultant moment equals 0, then the object rotates at a constant rate. Now, just like with forces, the most common constant rate is actually a kind of silly one. It's not rotating at all. So often, when an object is not rotating and the resultant moment is 0, it will continue to just not rotate. Okay, so let's try and use the principle of moments. Let's say that I tell you that this object here is not rotating. And then I say, what's this distance d? Well, it turns out you can calculate this using the principle of moments. So let's take moments around this point here. We could choose any one we like, but let's choose this one. Then what do we need to do? Well, we need to find the sum of the clockwise moments. Okay, so here clockwise, we have a force of 3 newtons at a distance of 2 meters from this point of rotation. So we have clockwise, we have 3 times 2. And the resultant moment is given by the difference between this and the anti-clockwise moment. So let's take away the anti-clockwise moment. What do we have here? We have 5 times some unknown distance d. Okay. And then I say, this object is not rotating. So what does that tell you? That tells you the resultant moment is equal to 0. So this is here, this equality here is using the principle of moments. And so altogether, this tells us that 6 must be equal to 5d. In other words, when the object is not rotating, this tells us that d is equal to 6 over 5. Done. Good. I won't personally be doing A-level biology and chemistry. I know there are at least A-level chemistry streams on the YouTube as well, on the channel, but I'm not sure when they are. They should be kind of scheduled. So you should be able to see them on the channel, actually. But I won't be doing them personally. I'm rubbish. I'm really rubbish at biology anyway. I actually didn't even get to do A-level biology, so that's kind of sad. Anyway, last concept we need before doing a couple of questions is a double concept that turns out to be a single concept. So we're going to give 2 definitions and then kind of a theorem at the end. So we're going to define the center of mass and then the center of gravity, and we'll find that they're actually the same thing. So first of all, the center of gravity. The center of gravity of a body is the point from which its weight appears to act. Okay, so for example, let's imagine we have some kind of a uniform body, constant density everywhere across this rod. Then, well, there's some mass over here, and this bit's being pulled down by a weight here. There's some mass over here. This bit's being pulled down by some other weight here, etc., etc., etc. When I consider all of these forces together, they essentially appear as if it's just one big force acting through the middle of this object. Okay, so this would be the center of gravity here, just the center. Again, similarly, if I have a uniform object here, same density everywhere, the center of gravity is just going to be the center of the object, essentially. So now let's talk about the center of mass. The center of mass of a body is the point that, let's say where, the point where if a force acts, it will not cause a rotation. So this is quite interesting. Let's take a look at an example. Well, let's say I've got an object here, this rod again, and I decide I want to push it somewhere, give it a push to get it moving to the right. Well, if I push it anywhere other than the center, then actually this push is going to cause it to spin as well. However, if we push it directly in the center, it won't spin. I mean, which way would it spin, for example? So it won't spin. And so this point here would be the center of mass. Notice again, it's just the center of the object. So it turns out that this is very general. The center of mass and the center of gravity, even when you don't have uniform objects, they are always in the same location. Good. Okay, so we're going to have a go at a couple of questions. How's everyone feeling about this stuff? Okay, nice. We might only have time for the one question, actually. We'll see how we get on. Okay, let me know if you have any questions about this stuff. So let's have a go at this one. Figure 2 shows an apparatus used to locate the center of gravity of a non-uniform metal rod. Okay, I'm glad. Okay, so this object is not uniform. The rod is supported horizontally by 2 wires, P and Q, and it's in equilibrium. State 2 conditions that must be satisfied for the rod to be in equilibrium. Okay, so the point now, usually when you're asked this, you would just say, okay, the force needs to be 0. The point is that now we're thinking about rotation as well. We need to also say that the total moment should be 0. So the resultant force should be 0. And second, the resultant moment should be 0. So both of these you need for what we're now going to call equilibrium. Okay, part B. Wire Q is attached to a Newton meter. Okay, here's wire Q. So the force on the wire, the force the wire exerts on the rod can be measured. We'll measure it here. The reading on the Newton meter is 2 newtons. Let's draw it in. And the weight of the rod is 5 newtons. Okay. Calculate the force that wire P exerts on the rod. Well, we're allowed to assume it's in equilibrium, so the total force should be 0. Well, we have 5 going down, then we have 2 newtons from Q, and then we have some unknown amount from P. So altogether, the amount from P must make up to 5 overall. So P must be 5 minus 2. P has got to be 3 newtons. Now we're asked to find the distance D. And this is about using, so far we've used this part of equilibrium. Now we're using this part of equilibrium, which means we're not rotating. So if we want to find the distance D, let's use this point here as the point we're taking moments around. Then we have 5 times D going clockwise. And we know that that needs to be balanced by 2 multiplied by 90 going in the other direction. So if you rearrange this, you'll find that D should be equal to 2 times 90 divided by 5. And so if you chuck that into a calculator, you should find it's 36. And because we chose centimeters here, we also have centimeters here. Good, okay. Right. So we're nearly there. Let's see what we have. Yeah, so we'll just go through this last question pretty quick. So we were asked to define the torque of a couple before, and the torque was given by the force of the size of either force times the separation between them. Okay. Why is the moment of a force and the torque of a couple have the same unit? Well, they are both given by a force, which is in newtons, times a distance, which will give you the meters part. Distance in meters. Okay, finally, the weight of the plate is 6 newtons. With the plate in the position as shown in figure 4.1, calculate the clockwise moment of the weight of the plate around an axis through point P. It sounds complicated, but we just have to be careful to go back to the original definition of a moment. So we've got this weight, this 6 newtons, and we want to know its moment around point P. So we just need to know the perpendicular distance between the line of action of force and this point. And that's going to be this distance here. And this distance here is 0.4 meters, just as it is down here. So the moment is given by the 6 Newton force times the 0.4 meters. Altogether, that gives you 2.4 Newton meters. Finally, we're asked to explain why the moment of the weight reduces to 0 when the plate reaches the bottom of the swing. So it's going to swing down because of this moment. It's going to rotate. And then eventually it's going to stop. The moment is going to become 0. So why is the moment 0 when suddenly we have a point P here and then the center of mass is essentially underneath it? Well, then the distance between where the weight is acting is 6 newtons and the point that we're calculating around is going to be 0, so the moment will be 0. So weight, perpendicular distance between P and weight is 0. Good. So hopefully this is making sense to everyone. You should now be able to talk about resistive forces. You should be able to define moments in center of mass, and then use the fact that an object isn't rotating, for example, to find the distance of action between some force and some point. So let me know if you have any questions for me. In the meantime, I have a couple of things to mention. You asked about, I know there's a question about web classes that are coming up. So here's a couple that are coming up. We've got A-level biology. So indeed, we do have those soon. In fact, next week, A-level biology. Same for, oh no, not next week, a little while away. We've also got maths and chemistry and then more chemistry. Okay, so I'm going to let you know now, we do have that coupon code for 25% off of any of the courses on the website. So I'm just going to show you now a bit of what the courses are like on the website, so you can see what we're up to. So I'm just going to come away for a second. So just to mention, to start with, essentially on the Stat Revise website, we've got a few things going on. We've made a load of video courses. So rather than using a revision guide or a textbook, you can learn everything by video. So these are bite-sized teaching videos. And then we've been doing a load of stuff, including like making our own revision guides. We've been doing a load of stuff to kind of improve the courses, which I'm going to show you now. So I'll just take a second to get that up. Okay, so you should be able to see the Snap Revise website now. So I'm going to go into the physics course because why would I choose any other? Let's do AQA just for fun. And let's see if we can easily find a mechanics thing to go for. What have we got here? Motion along a line. Okay, sadly, I've done some of these before, so we'll do something else. Let's just do momentum. So let's say I want to learn about momentum. Rather than opening the page to go to the momentum part of my textbook, I'm going to actually start with a quiz. And the point in the quiz is not necessarily just to check how you're doing, but it's actually to kind of design the course a bit around essentially your actual needs. And hopefully in that way, like improve the speed at which you can get through the course and make sure you spend all your time doing the stuff that's important for you. So here's the diagnostic quiz. It's not a test as such. So I'm going to try a load of random questions. That was pure luck that I got that right. Hopefully I'll get some wrong. Let's see how I do. Okay. Okay, now I'm not doing so well. Okay, 2. You can take 2. Maybe I'll get lucky with 1 more. Yeah, 3. That's perfect, actually. 4. Okay, pure luck, but I got 57%. Okay. So once you've done this, the point is, okay, great. So here's some things you know, here's some things you don't know. But here's where things really get going. Now, when we go into the actual course, there's essentially everything that we don't need to look at is highlighted in green. And the stuff that has kind of parts that we need to check up on are in orange. And in fact, even when you go into the course, into the video, you can just skip straight to the orange parts, the parts which you didn't get correct in the test. So the idea here is to just like speed up the course and make sure you spend the time on the stuff that's most important. We've also been making exam packs and been going through, we've been filming ourselves going through exam questions so you can see how we try and work through them, and in particular how we try and extract the meaning from the question, because that's often one of the hard bits. So separately, we've also got exam packs, just a load of exam questions that we've been coming up with, and our own revision guides for you to look at. So you can go into these courses, and the code that we have will give you 25% off for these courses. So I'd love to see you there. It'd be great if you can take a look. We're also doing web classes, and in fact, I'm about to start one on particles in magnetic fields right now. So let's just take you to web classes so you can see what we're doing here. So I'm just about to do another couple of web classes now. One of them, I'm going to be going through material like I was doing here. And in another one, I'm going to be doing a drop-in session where people can just come in and ask any questions that they're stuck on, and we just work through them together. So this is a separate deal to all of the courses stuff. So they're separate memberships, but there's also all of this web class stuff where we're essentially trying to make tutoring a tutoring style service. So it'd be great to see you at either of those. And I must actually get off now to go and do my next video web class. So thanks very much for coming, everyone. I really appreciate it. And we'd love to see you at a future class or on the courses. So here's the code for 25% off the courses. And yeah, thanks very much for sticking around. And thanks very much for all the engagement in the chat. It made it a really nice session to teach. So yeah, well done, everyone. And I hope it was useful. Okay, thanks very much for coming, everyone. Bye.